Let us have a look at some problems asked so far in GATE as well as engineering services examination on half wave rectifier. Okay. See, look at the first question. A half wave rectifier is used for uses a forward resistance RF. The source voltage is Vm sin omega t and the load resistance RL. The DC current is given by. What is the equation of DC current? You see, they have not mentioned anything about the internal resistance of the secondary winding. So let us take Rs is equal to 0. Okay. What is the formula for IDC in a half wave rectifier? The DC current they are asking. So IDC is equal to Im by pi, where Im is equal to Vm by Rs plus Rf plus Rl multiplied with 1 by pi, in which Rs is not given, it is 0. So what is your final answer? Vm by pi into Rf plus Rl. From the given data, we can take it so. So option B is correct. A very simple question it is. Look at the second question. The forward resistance of the diode shown in the figure is 5 ohms and the remaining parameters are same as those of ideal diode. Okay, diode forward resistance is given. If Vi is equal to Vm sin 314t, the DC component of the source current is same thing, right? So DC current they are asking a half wave rectifier. Diode forward resistance Rf is given as 5 ohms. Okay, data is given. Earlier problem, right, Rf and Rl values were not given. Now the values are given. So what is IDC? IDC is equal to Im by pi, where Im is equal to Vm by Rs plus Rf plus Rl multiplied with 1 by pi, in which anyway Vm value is not given, we can take it as it is. Rs is 0 and Rf is 5 ohms and Rl is equal to 45 ohms. So the final answer is Vm by 50 pi. So option A is correct. So very simple question. The output VO of the diode circuit shown in the figure is connected to an average DC voltmeter. Okay, average meter or DC meter both mean the same. Okay, so the reading of the DC voltmeter in volts, neglecting the diode drop, neglecting the voltage drop across the diode is. Okay, what is the reading of the DC meter? Anyway, VDC they are asking. Ideal diode it is mentioned. Neglecting the voltage drop across the diode means RF is 0. We can take it. Then DC, VDC is equal to IDC into RL. IDC is equal to Im by pi into RL. Im is equal to Vm by Rs plus Rf plus Rl multiplied with Rl by pi. So here anyway Rs is 0, neglecting the drop across diode means Rf is also 0. Now I can cancel. So once these two terms are 0, then I can cancel RL and it is Vm by pi. Okay. And what about Vm? It is 10. So the answer might be 10 by pi. That's it. This is what we can take. Anyway, right, instead of writing all those things, even what we can take is V output is equal to 10 sin omega t over the interval 0 to t by 2, and it is 0 over the limits t by 2 to capital T. Right. So our output waveform comes like this, and its peak amplitude is 10 volts. So what about VDC? VDC is equal to peak amplitude by pi. Even in this way also we can write it. It's a simple thing. Okay, the basic formula I had wrote it, in that I substituted the values, nothing else. As it is ideal diode, V output is equal to 10 sin output is equal to input from 0 to T by 2, and from T by 2 to capital T, the output is 0. So output has a peak amplitude of 10 volts. So the average value or the reading of the voltmeter, it is peak amplitude by pi. It's as simple as that. A half-wave rectifier has an input voltage of 240 volts RMS. So V secondary RMS value is given. It is 240 volts. Then if the step down transformer, sorry, it's not V secondary, V primary, sorry. The half-wave rectifier has an input voltage. If the step down transformer has a turns ratio of 8 to 1, okay, what is the peak load voltage ignoring diode drop? Okay, so here the secondary voltages or voltage is not directly given. Instead, it is given the primary voltage 240 volts, and turns ratio is 8 to 1. So what about the RMS value of secondary voltage? So V secondary RMS, it is equal to V primary RMS by, right, 8. I can write, because the turns ratio V primary by V secondary is equal to N1 by N2. We are well aware of it. It is 240 by 8. It is equal to 30 volts. RMS value of secondary voltage. So V secondary peak amplitude is equal to RMS is equal to peak amplitude by root 2, or peak amplitude is equal to V RMS multiplied with root 2. That is 30 root 2. Root 2 is 1.414. So it is 30 into 1.414. 14 3s are, right, 42. So option D is correct, 42 point something. It's very simple. Okay, that is the peak load voltage they are asking, peak load voltage, because here ideal diode, as the diode is ideal, V output is equal to Vs over the interval 0 to T by 2, and it is 0 over the interval 0 to capital T. So input is V output is equal to V secondary. Obviously output peak amplitude is equal to peak amplitude. It is V output peak. Secondary amplitude, peak amplitude, amplitude of the secondary voltage and output voltage are one and the same. Next, the power supply has, a power supply has 4% voltage regulation and the open circuit voltage of 48 volts DC. The full load voltage is, okay, so it's a formula based question. The percentage regulation is equal to VDC no load minus VDC full load by VDC full load into 100, and its value is given as 4%. So no load voltage is open circuit voltage, means no load voltage. It is 48 minus VDC full load by VDC full load into 100. It is equal to 4%. So 425. So 48 minus VDC full load, it is equal to, or I can do one thing. Let me take it so 48 into 25 minus VDC full load into 25 is equal to VDC full load. So VDC full load is equal to 48 into 25 by 26. I am directly writing 25 times VDC full load. If it is taken to the right hand side, then the total, it becomes 26 VDC full load. So how much do we get? Its value is no doubt less than no load voltage, okay, less than 48 voltage, 48 volts. So if you look at all options, all are less than 48 only. Okay, but that is almost close to no load voltage and full load voltage. So regulation is 4%. So there is no much difference between no load and full load, right? I am doing it without using the calculator. The answer might be, right, around 46.15 volts, right? The students can calculate and check it. I am directly writing it, right? The regulation value is less, so definitely no load voltage is somewhat close to the full load voltage, maybe, right? Your answer is 46.15, right? Without using calculator I'm doing it. So okay, it comes. Next, a power supply has a full load voltage of 24 volts. What is its no load voltage for 5% regulation? So full load voltage is 24. So it is greater than, right, full load, no load voltage is greater than full load voltage. And regulation is very less. So close to 24 but greater than. If you look at the options without calculations blindly, we can take the answer as 25. Okay, it should be greater, only one value is greater and close to that. Okay, let us check it. The percentage regulation, it is equal to no load voltage minus full load voltage by full load voltage multiplied with 100. No load voltage is not known, minus 24 divided by 24 into 100, it is equal to 5%. So 5 20s, I can take the brackets this way. So 20 into VDC no load minus 480 is equal to 24. So VDC no load is equal to 480 plus 24, it is 504 by 20. So it is 20, it is 25.2 something, you will get it. So rounded to the nearest integer means it is 25 volts. That's it. Okay, it's as simple as that. Next, a DC power supply has a no load voltage of 30 volts and full load voltage of 25 volts at a full load current of 1 ampere. What is its load resistance and load regulation? So the load resistance means RL, it is equal to VDC full load by IDC. Okay, we can write this current due to a load resistance RL. So VDC full load, how much? VDC full load, it is 25 by load current 1 ampere, so it is 25 ohms. Okay, so either B or C we can think of. Then what about the percentage regulation? Percentage regulation, VDC no load minus VDC full load by VDC full load multiplied with 100. It is 30 minus 25 by 25 into 100. 25 4, 30 minus 25, 5 into 4, it is 20%. So option B is correct. So questions are very, very simple actually. 8. A diode with forward voltage Vf is equal to 0.7 volts is connected as a half wave rectifier. Okay. The load resistance is 600 ohms and the RMS or AC input, okay, is 24 volts. So the RMS value of secondary voltage RMS, it is 24 volts. So that peak amplitude of the secondary voltage will be equal to 24 root 2. We know that RMS is equal to peak amplitude by root 2, or peak amplitude is RMS into root 2. Okay, the secondary voltage peak amplitude. Then what about the peak amplitude of the output? Okay, if you take the half wave rectifier, the diode forward resistance 0.7 volts and it is a secondary. So V output is equal to V secondary minus the diode forward voltage. So output peak amplitude of the output they are asking, it is equal to V secondary peak minus Vf, the diode forward voltage. It is 24 root 2 minus 0.7. Okay, 24 root 2, 24 into root 2 is 1.414. So 14 fours 56 approximately I am writing it. 5, 14 to 28 plus 5, 33. 33 point something. Okay, so here this value option C might be correct. Approximately I am writing it. Okay, it's minus 0.6 no. It is 33.6 something minus 0.7. So 20. Anyway, you can do the calculations and I don't want to do all such things. It comes close to 33.24. Okay. Determine the peak load current. Okay, IL. IL is equal to V output by RL. We can write it. And IL peak means V output peak by RL. Output peak amplitude, right? Anyway, we have got it like 33.24 something. 33.24 by RL. It is 600 ohms. Okay, it comes to be around 55.4. Okay, it comes to be around. Okay, place is not sufficient. I will do it in the next page otherwise. Because this is our IL. So IL is equal to V output by RL, we can write. And IL peak, it is equal to V output peak by RL. It is 33.24 by 600. It comes to be around 55.4 milliampere. Okay. Option A is correct. Determine the diode reverse voltage. Means peak inverse voltage they are asking. Okay, peak inverse voltage. So when the diode is reverse path, peak inverse voltage is equal to V secondary peak. So how much it is? It is 24 root 2. It's slightly greater than 33.52 something. Greater than 33.24. So 33.9. Option B is the answer. That's it. Next, the figure shows a half-wave rectifier circuit with input voltage Vi is equal to 10 sin 100 pi t volts. Assuming ideal diode characteristics with 0 forward voltage drop and 0 reverse current, the average power consumed in watts by the load resistor RL is. What is the average power consumed? Average power means DC power they are asking. Okay. So, if you take PDC is equal to IDC square into RL, or write IDC square into RL, IDC is equal to Im by pi whole square into RL. What is Im? It is, I can write it like Vm by RL, because ideal diode and there is no internal coil resistance. Okay, we can write it so, into pi whole square into RL, or it is Vm square by pi square into RL. So what is Vm? It is 10. So 100 by pi square, it is approximately 100 into RL is 100. It is 0.1 watt. Right. This is the average power. We can see. Suppose they ask, what is the AC power? Then what do we write? IRMS square into RL. We can take so. AC power, if they ask AC power, okay. AC output power means IL square into RL, that is IRMS square into RL. IRMS is equal to Im by 2 whole square into RL. Im is equal to Vm by RL. It is equal to Vm square by 4 into RL. AC output power. Okay. So Vm, how much is the value of Vm? It is 10. So 100 by 4 into RL, it is 100. It is 0.25 watts. Okay. This way we can write it so. As it is a half-wave rectifier. The maximum efficiency of a half-wave rectifier is, efficiency is 40.6%. Option B is correct. It's a straight formula based question. For the circuit shown with ideal diodes shown in figure, the shape of the output voltage for the given sine wave input will be, okay. So let me take it as D1 and this one as D2. How can we draw this circuit? You see, from the positive terminal of input, diode D1, and from its cathode to, right, it is a resistor RL. And other end of RL, right, okay, of course, it is negative, and other end of RL, it is positive. I can take, which from this we have the diode D2 and input. See, the same circuit, this circuit can be redrawn in this fashion. It is V output. Both are one and the same. Just they twisted it to confuse us. Then what happens? During positive cycles, both the diodes conduct. Okay. So in this circuit, right, just observe this circuit and this circuit are one and the same. Positive cycle, positive half cycle, right, means polarities I can take this way, both D1 and D2 are on and they act as short circuit. So that V output is equal to minus Vi. See the polarities of output, top, bottom to top. So during positive half cycles, both D1 and D2 are on. So they behave like short circuits. RL V output. So V output is equal to minus input. That's it. If polarities of output are from top to bottom, then V output is equal to input. But here V output is equal to minus V input. And during negative half cycles, Exactly opposite action. No diode conducts. So when negative cycle comes like this, so means it is minus and it is plus. Anode of D1 is connected to the negative terminal off, and cathode of D2 is connected to positive terminal. D2 is also off. So both the diodes will be off during negative half cycles. So that both D1 and D2 are off. So what about V output? It is simply 0. So if you observe the overall waveform, how can we get it? How do we get it? So when input is positive, that time output is negative. V output is equal to minus Vi. And input is negative, that time output is 0. So input is positive, output is minus Vi. Input is negative, output is 0. So this is how we can see the output waveform. So option, this one we can write here A, B, C and D. Option C is correct. Next, in the circuit of the figure, assume that the diodes are ideal and the meter is an average indicating meter. This is an ammeter which is an average indicating meter. The ammeter will read. What is the reading of the ammeter? Okay. During positive half cycles, what happens? Definitely D1 is on and D2 is off because its anode is connected to positive terminal and cathode is going towards negative terminal. D2, its cathode is going towards positive terminal of the supply and its anode is going towards the negative terminal of the supply. So D2 is off. So during positive half cycles, D1 is on and D2 is off. D1 almost acts as short circuit. It is our average indicating meter. Ten kilo ohm, 10 kilo ohm and input. So the current will be flowing in this fashion. I can say this is IL. So IL is equal to V input by 10 kilo ohm. Assuming the internal resistance of the diode is 0 as well as the ammeter's internal resistance is also 0. V input by 10 k. So what is V input? It is 4 sine omega t. So 4 sine omega t by 10 kilo ohm. It is 0.4 sine omega t milliampere. Okay. And during negative half cycles, opposite action, the diodes will be D2 is on and D1 is off. D1 is off and D2 is on. Ten k, 10k, 4 sin omega t or V input. And what about the current through the meter? It is simply 0. Entire current will flow through this 10k only, but not through this 10k. No current flows through the meter. So IL is 0, or current through the meter. Let me take that as IL. IL is 0. So it is now behaving like a half wave rectifier. If you take IL waveform, it comes this way with a peak amplitude of 0.4 milliampere. Then what about the ammeter reading? Means IDC. The reading of the ammeter means IDC. It is peak amplitude by pi. 0.4 by pi milliampere. That's it. So option D is correct. The input impedance of the permanent magnet moving coil PMMC voltmeter is infinite. Okay. Assume that the diode shown in the figure below is ideal. The reading of the voltmeter is okay. It's a DC meter. PMMC, it gives a DC reading. Then what about the reading of the meter? That's what they're asking. Okay. See, during positive cycles, what happens? The diode is on and it acts as short circuit. So, during positive half cycles, diode is on. So, the equivalent circuit is this way. Anyway, right, it is a 100 ohms, 1 kilo ohm. Entire current flows in this direction. V output is 0, right? It acts as short circuit, and if I take this as my V output, anyway, V output polarities are from bottom to top. Output is 0. Okay. Then during negative half cycles, I'll write it in the next place. What happens to the diode? Diode becomes off. Once the diode is off, then once the diode is off, the diode acts as open circuit. It is 1 kilo ohm, 100 ohms input. Okay. Then how will the current flow? Actually, right, even though I'm showing the polarities this way, the actual polarities will be this. So the direction of the current flow, to see the direction of the current flow, I am taking it so. Okay. Or we can even write it like V output is equal to minus V input by, because of the polarities of output, right? From these polarities I am speaking. V output is equal to, okay, minus V input by 1 kilo ohm plus 100 ohm or 0.1 K multiplied with 0.1 kilo. Okay, like this we can write it. So how much do we get? It is 100 by 1100, so minus V input by 11. Then what about okay, what V input, its value is 14.14 sine 314t by 11. Once you get the output equation, positive cycles, it is 0, and if you take the output waveform, positive cycles, the output is 0, And negative cycles, input is negative but the output is positive, because input is something like this. Input is negative, minus of negative, output will be positive. This way we can see the output waveform. Equation is looking like minus Vi, but as the input is negative, negative of input, it is positive. Okay. So, it is like a half wave rectifier. And what is the average value of half wave rectifier? The meter gives the average value. So, VDC, it is equal to V output peak by pi. Okay. Of course, this statement is true only for T by 2 to capital T. Don't get confused. Okay. So, what about the peak amplitude? 14.14 by 11 into pi. Okay. So, how much do we get? If you calculate it, no negative sign, sorry, here it should be positive, because output voltage is positive only. Sorry. (0.41) or 0.4 volts. Okay, so option D is correct. That's it. This is how we can write so. Okay, we know the output waveform, how it comes. Then we can calculate the DC meter reading or VDC. Indirectly they are asking VDC. The meter gives the DC value. It is peak amplitude of the output by pi. That's it. Next, the RMS value of a half-wave rectified symmetrical square wave current of peak to peak amplitude of 2 amperes is. Okay. So, what they are asking is secondary voltage, for example. Peak to peak amplitude is 2. So, and symmetric 0 T by 2 T. This is passed through a half wave rectifier. Okay. The RMS value of the half wave rectified symmetrical square wave current of peak to peak amplitude. Okay. So, in this the current is right, actually current of amplitude we can take. Peak to peak we need not worry about writing. Okay, it's not secondary voltage, right? Or we can write here 1 ohm normalized resistance. So, if that is the case, what about IL? IL is equal to, or this secondary voltage V output will be something like this. Right, it is 1 volt minus 1 volt. So, 0 to 1 volt. It is V output. We can take. And what about IL? IL is also a similar way. One ampere, 0 T by 2 and capital T. Okay. So here the question should be given written properly, right? Peak to peak amplitude of 2 amperes. Okay, peak to peak amplitude according to the given data means, okay, this here I assumed normalized resistance and all, right? And it has a peak to peak amplitude of 2 amperes. If that is the case, how the waveforms appear? Based on that, let me do otherwise. Okay, the load current will be, right, definitely symmetric square wave. Here it's not a symmetric square wave, as it is mentioned symmetrical square wave. Okay, symmetrical means T1 is equal to T2. Okay, in that context, what we can write here, right, instead of these things, let me take on another way. Okay, the load current of half wave rectifier is like this, 0 T by 2 capital T. Okay, it might be this way. If that is the case, according to this, right, anyway current cannot be negative. Once you pass a signal through half wave rectifier, its current should be either a positive or 0, minimum of 0. It cannot be negative. Okay, peak to peak amplitude means I can take 2 amperes. Then what is its average RMS value? RMS value of a symmetric square wave of peak amplitude A, it is equal to A only. But if the amplitude is like this, then the RMS value is peak amplitude by root 2. Okay. Okay, let me do it otherwise. IRMS is equal to root mean square. 1 by T. 0 to T by 2, its amplitude is 2. So I can write 2 means 2 square, 4 dt, plus from T by 2 to capital T, it is 0. Anyway, this term we can eliminate. It is equal to square root of 1 by T into 4 into constant into T by 2. We can write 2 cancel, and it is equal to root 2. IRMS is equal to root 2 amperes. So option A is correct. Okay, as it is mentioned peak to peak amplitude. If they mention peak amplitude also in this example, peak to peak or peak amplitude are 2 amperes only, because its minimum amplitude is 0 and maximum amplitude is 2 amperes. You take peak amplitude or peak to peak amplitude, the result is same. Okay, option A is correct. Or whenever you have a waveform of this kind, the RMS value is peak amplitude by root 2. If you remember the formula in signals and systems, 2 by root 2, that is root 2 amperes only. For this kind of waveform, the RMS value is peak amplitude by root 2. Even though it is a square wave, it's right. The answer is similar to the sine wave. Sine wave peak amplitude is A, but sine wave peak to peak means 2A. That's a different story. Okay. Right. See this question. In the circuit shown, Vs is a square wave of period capital T with maximum and minimum values of 8 volts and minus 10 volts respectively. Assuming that the diode is ideal and R1 is equal to R2 is equal to 5 ohms, the average value of VL is rounded off to 1 decimal place. What is the average value of the output voltage? Anyway, the resistors are 5 ohms each. So during positive cycle, or when we 0 to T by 2 input is positive, diode is off, and the equivalent circuit is something like this: 0 to T by 2. Diode is off. So it is 5 ohms. Each one is 5 ohms, I think. Both are equal. R1 and R2 are equal. Okay. Then VL is equal to V input by 2. Entire current flows this way. So, and V input is equal to 8. So, it is 4 volts. And from T by 2 to capital T, during the next half cycle, diode is on. Right? Cathode is connected to the negative terminal and anode is connected to positive. Diode is off. So, sorry, diode is on. Once the diode is on, it acts as short circuit. Short circuit parallel with short circuit, that is short circuit. V output is equal to input. What is V input? Minus 10 volts. Okay, so how do we get the output waveform? Four volts minus 10 volts. So average amplitude, average value means area under the curve. Okay, so VDC or average, it is nothing but, right, according to the, just I'm writing the formula, not required, we can do this problem directly. 1 by T integral 0 to T V output dt, or area by time period. Area means, let me take this as A1 and this as A2. A1, it is 4 into T by 2 plus second one minus 10 into T by 2. Whole thing divided by capital T. So 2 minus 5, that is minus 3 into T by T, it is minus 3 volts. That's it. The average value is negative. What to do? It's possible. It's not mandatory that the average value should be always positive. Right? Rounded up to 1 decimal place. Anyway, it is minus 3 volts. That's it. This is how we can do this problem. So these are some of the questions asked in previous GATE papers as far as half-wave rectifier is concerned.